In this lesson, I'm going to talk about variance and standard deviation of a random variable. We're also going to look at linear transformations and combinations of a random variable or multiple random variables. So let's start with the discussion of variance and standard deviation of a random variable. So if x is some discrete random variable, and we'll consider other kinds of random variables in a future lesson. So if x is a discrete random variable, recall that the mean is also known as expected value of x, or expected x being the random variable. And of course, we know this is one way to calculate the mean, which is to multiply each value times its frequency, and then add those all up, and then divide by the total number of values. Or in other words, if I factor out that 1 over n and put it in the front, then it's 1 over n times sigma of xi fi. Well, I can now, since this is a sum, I can distribute 1 over n into every single term of this sum, and I can write it this way: sigma of xi times fi over n. But fi over n is the frequency divided by the total, which is just the probability of it occurring. So really, mu, or the expected value, is just sigma of xi pi. Now, we've done this before, so I'm just reminding you of a way to relate this version of mu to the version of mu, or expected value, that we've talked about already. So now let's consider variance. Now you may recall that this is the formula for variance if you have frequencies. So you take each value, subtract off the mean, square that value, and then you do that how many ever times that particular value occurs. In other words, multiply by its frequency so that you can do repeated addition. And then you add all of those up. And then when you're done, you've added up all of these squared deviations, you divide by the total number of values. But then I can do the exact same thing where I factor out the 1 over n and then I distribute it in. And once again, I'm going to get my fi over n after I've got my xi minus mu quantity squared. Now, so this basically becomes variance of x, which is equal to the sum of the xi minus mu squareds times the probability of each of those xi's. And of course, then we add them all up, as I said. Now, if you think about it, this here, this was sigma of xi times its probability, and that ended up being expected value of x. Well, now this new one is now sigma of the xi minus mu quantity squared values times each of their probabilities. So this is just the expected value of x minus mu quantity squared. And this is the way we write variance. This is an alternate way of writing variance, and that, again, in this case, relates to a discrete random variable. And again, what you're doing is you're taking each value, subtracting off the mu, squaring it, and then multiplying it by its probability, because that's how you do expected value, and then add them all up. And that's exactly what we want to do. Take each value, subtract the mu, square it, multiply by its probability, and then add them all up. And that's how you're going to get your variance. Now, standard deviation, of course, is just the square root of the variance. So it's the square root of the expected value of the x minus mu quantity squared expression. Now, this is not a very convenient calculation to have to do. Take every value, subtract off the mean, square that, multiply that answer by the probability, and then start adding all of those up. That gets rather tedious, but it turns out that there is a shortcut, which I will prove later on in this lesson. But for right now, the more practical way to calculate variance is to do the expected value of the x squared minus, and then the square of the mean. So let me explain what this is. Again, just like over here, I said, okay, when I'm multiplying xi times pi and then adding them all up, that's expected value of x. When I'm multiplying out xi minus mu quantity squared times pi and then adding all of those up, that's the expected value of x minus mu squared. When I'm trying to do expected value of x squared, I'm just doing the sum of the xi squares times pi. That's the expected value of x squared. And then, of course, after that, I'm taking away mu squared. So what you do is you take each of the values that you have and square it Then you multiply by the probability and you add those numbers up, and then afterwards subtract off the mean squared. So this is a little easier because it does not require you to do the subtraction from the mean for every single value. You can just take each value and square. That's a simpler calculation. Multiply those by their probabilities, add those up, and then subtract mu squared. Now this is going to be your convenient way of doing things moving forward. So remember this formula rather than this formula as far as variance is concerned. So here's an example where I'm going to use that formula for variance. The question here was actually to find the standard deviation of the random variable x. I'm not going to do that first. Typically when you're doing manipulation, variance is a lot easier to work with, and then you just square root it to get standard deviation. So you basically work with variance to do whatever manipulation you need to do, and then at the end take a square root to get into standard deviation. Reporting standard deviation is a more useful value, but performing calculations is a lot easier to do with variance. So anyway, here's the random variable. You may recognize this from a previous video. These were the number of magazines that various customers purchased, and these were the probabilities that many magazines were purchased by the customer. So 23% of customers purchased one magazine, 38% purchased two, etc. Previously, we had found that the mean number of magazines purchased by these customers was 2.39. So I'm going to use this to calculate the standard deviation. But in order to do that, I'm actually going to start by calculating variance. And I'm going to use the better formula for variance rather than the complicated one. So I'd rather not have to do 1 minus 2.39 and square that number, 2 minus 2.39 and square that number, etc. This is going to be an easier calculation, and you'll see what I mean in a second. So what we do to do expected value of x squared is we find all of the x squared values, so 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and multiply each of those squares by their probability. Remember, expected value of x would just be 1 times 2.23, 2 times 0.38, etc. But expected value of x squared will be 1 squared times 0.23, 2 squared times 0.38, etc. So that's what I've done over here. I've added each of their squares times the corresponding probabilities, and that's this expected value of x squared. And then I have to subtract off the mu squared, which is the 2.39 squared. Now I've done that on my calculator, and I ended up with 1.2579. Now I've kept lots of decimals because that's the variance. That is not what we were asked for. We were asked for standard deviation. So standard deviation is going to be the square root of 1.2579. And that's the one I'm going to round to my usual 3 sig figs, so 1.12. So the standard deviation of this random variable is 1.12. And you can see, apart from multiplying by these ugly probability values, calculating expected value of x squared is something you could do manually, again, assuming those probability values were easier to manipulate. Because the random variable values are typically going to be nice and convenient, like 1, 2, 3, 4, or 5. The probabilities are going to be the ones that are ugly. But if I want to subtract off 2.39 each time first and then square, that's a pain. So anyway, this is an example of the shortcut variance formula at work. Let's look at linear transformations and combinations of random variables. So first, let's let x be some random variable, and then a, b, and k are going to be real numbers, and they're going to be constants. So the expected value of a constant is a constant. So what do I mean by that? So if you're doing an experiment where the result is always you're going to get a 5, that's a constant. The result is always that constant. Doesn't matter what you do, you're always going to get a 5. Well, then the expected value of doing the experiment is you're going to get a 5, right? So the expected value of a constant is a constant. There's no variation. You are going to get what you expect. The next one is the expected value of a times some random variable. So consider this. Let's say we were to toss a coin. So the expected value of tossing one coin is to get a half number of heads. Now, of course, you will never get a half number of heads, but on average, when you do this tossing of a coin lots and lots of times, you will get a half number of heads on average, because half the time you'll get heads, half the time you get tails. However, the expected value of tossing 10 times a coin is that you're going to get 5 heads. How do we get 5? 10 times the expected value of getting 1 of tossing one coin, which was 1/2. So 10 times a half gave you 5 heads. So whatever the expected value of your random variable is, either you multiply the random variable by the coefficient, or you multiply the expected value by the coefficient, you're going to get the same answer either way. Another way to think about it is, let's say I told you that the expected distance of throwing, I don't know, a baseball for me is, I'm going to make something up here, 27 meters. Well, all right, fine. So you know that the expected value of x is 27 meters. However, let's say I wanted you to give it to me in centimeters. Well, one way to do that is to make me do the experiment a whole bunch of times and measure the centimeters instead of meters, and now do the average of that. Another way to do it is to say, well, if I expected to get 27 meters, when I multiply 27 meters, my expected value measured in meters by 100, that will literally just give me the expected value in centimeters. So it doesn't matter what I multiply by, I measure in centimeters at the beginning, or if I just take my old expected value and multiply by 100, so I convert the meters for my expected value into centimeters. So that's what that one's doing. And then if g and h are functions of x, and we've seen that before. For example, variance is a function of x. It's the expected value of x minus mu quantity squared, so that's a function. So if you have expected value of g of x plus h of x, it's okay to separate out the expected value of the g of x plus the expected value of the h of x. So for example, let's say we perform the experiment where I pick up a baseball and I throw it as far as I can, and then my brother walks to wherever the baseball is, and then he throws it as far as he can after that. So let's say we said that I had an expected value of how far I can throw a baseball, which would be 27 meters. And let's say my brother, who is much stronger than me and much bigger than me, can throw it with an expected value of, let's say, 50 meters. Now the question is, what's the expected total distance when we put them together? So either I can throw a baseball and then he can throw a baseball, and we can do that a whole bunch of times and see what happens for the total and then find the expected value of that. Or I could just say, well, I'm expecting to be able to throw it 27 meters. He's expected to be able to throw it 50 meters. So when I add the two expected values together, we expect that in total, we will get the ball 77 meters from the starting point. So you don't have to do the experiment first and then average those, or do the expected value. You could just take my expected value plus his expected value and work it out that way. So now let's look at the expected value of ax plus b. Well, I've got the expected value of ax, and then I've got the expected value of b. But remember that a and b were constants. So this is a coefficient. I'm multiplying my random variable by some number every time. So I can pull that coefficient out, and I can get a times expected value of x. But then I'm also doing the expected value of a constant, which is just that constant. So this becomes a times expected value of x, and then plus b. So I can factor out the a, and I can separate out the plus b, and I could do it this way. So I don't actually have to perform each calculation for every single entry of my random variable. I could just use the old expected value, multiply it by a, and then finally add b. So here's an example of this one. So I want to compete with my brother in throwing a baseball, but I need a handicap because he can throw a baseball farther than I can. So in order to make it more fair, I'm going to give myself a handicap of, let's say, 2,225 centimeters. Now, I know that my expected distance of throwing the baseball is 27 meters. So either every time I throw the baseball, I have to convert to centimeters, and then I have to add, and I lost the number now, whatever that handicap was. Or I could just know that I have an expected range of 27 meters, convert that to centimeters by multiplying 100, and then add on the extra handicap that I had, and I can just do it once using my old value of my expected distance of throwing a baseball. So that allows me to do this more quickly. Now the final formula here is that the variance of ax plus b is going to be a squared times the variance of x. And I will be proving this formula in another slide. So here's a proof that the variance of x is really expected value of x squared minus mu squared. So we can now use that shortcut. So we'll start with what we know about variance, which is that it's the expected value of the x minus mu quantities squared values. In other words, take every value, subtract the mean, square it, and then find their average, which is what expected value does. Multiply them by whatever frequency, or multiply them by probability, or maybe add them all up and then divide by the number of values. It's up to you which way you want to do that. Okay, so I'm going to work with expected value of x minus mu quantity squared. Well, first of all, I'm going to square out that x minus mu. So it's going to be expected value of x squared minus 2x mu plus mu squared. Now remember that mu is a constant. Mu is the mean of this random variable, which is just a number. It's not going to change. It is a value. So I can work with these three terms, these three quote-unquote functions inside expected value and split them up. So really what I get is expected value of x squared and then minus expected value of 2x mu and then plus expected value of mu squared. Now, this is exactly the thing we want, so I'm not going to mess with it. I like the way that I got this out of this expression because that's part of my final answer. So I'm going to leave that alone, but I want to mess with these two now. Now, expected value of any constant is just the constant itself. So this is just going to become mu squared, and I got to play with this. So this is going to be expected value of x squared, and this is going to be plus mu squared. But this one over here, well, first of all, there's going to be a minus sign. Now, 2 times mu, those are both constants, so 2 times mu is the coefficient, and by the rules we just established, the expected value of some coefficient times a random variable, well, that coefficient can simply get pulled out. So minus 2 mu times expected value of x. So I essentially pulled that 2 mu, that coefficient, out in front and left myself with expected value of x. Now here's where it gets very clever. Expected value of x, that's just the mean of x. We have a name for that. It's called mu. So really what we're saying here is that we have expected value of x squared minus 2 mu times this new mu, which we just discovered, plus mu squared. Well, that's just minus 2 mu squared and then plus mu squared. Those are like terms. So really, we get expected value of x squared minus mu squared. And that is why this formula works for the variance of x. So that's now why we use that for the shortcut. So here's the proof that variance of ax plus b is equal to a squared times variance of x. So first we start with variance of ax plus b. And now ax plus b here is the random variable. So it's going to be expected value of whatever that random variable is squared minus the mean of that random variable, which is just expected value of that random variable, squared. So that's just the regular old variance formula for the random variable ax plus b. Now I'm going to do some squaring and moving things out of the expected value to make it work. So here I squared out the ax plus b, so I get a squared x squared plus 2abx plus b squared. And then I pulled out the a and the plus b from the expected value of ax plus b. So it's a times expected value of x plus b, but that stuff is still being squared. Now recall that expected value of x is just mu. So here I'm going to pull out all these coefficients and the b squared. So a squared expected value of x squared, 2ab expected value of x plus b squared. And then here I'm going to square out this a mu plus b to get a squared mu squared plus 2ab mu plus b squared. And then of course I'm subtracting, so I'm going to have to distribute the minus sign. Now once again, this expected value of x is just mu. So I have a squared expected value of x squared plus 2ab mu plus b squared, and then distribute the minus sign, minus a squared mu squared, minus 2ab mu, minus b squared. And you'll notice that the 2ab mu and the negative 2ab mu cancel, the b squared and the negative b squared cancel, so I'm left with just these two terms. And when I look at those two terms, and I notice that they both have a squared in them, so a squared is the greatest common factor. So a squared times the expected value of x squared minus mu squared. Now notice that expected value of x squared minus mu squared, that's just variance of x. And so this is a squared times variance of x. And therefore, variance of ax plus b is just a squared times variance of x. And that's my proof. Let me talk briefly about why this makes sense. So first of all, the plus b means you're going to move all the data in one direction or the other. When you take data and you just move it, let's say you add 100 to it or whatever it might be, the spread of the data is not changing, just all of the data is moving together. Now the A here does change the spread. So when you multiply all the data by 2, for example, you've doubled the spread. Everything is twice as far away from everything else as it used to be. Therefore, everything is also twice as far away from the mean. However, remember, variance measures the squares of the deviations, not just the deviations themselves. So the variance is now going to get multiplied by a squared, or in this case where I'm doubling, by 2 squared, or 4. So that makes sense that the variance of ax plus b should not get changed by adding and subtracting numbers, but it should get changed by multiplying by a number, and it'd be changed by a squared if a is the number you're multiplying by. Let's do an example. So x is a random variable with probability distribution given right here. The question is to find the expected value of x and then the variance of x. So let's do that first. So the expected value of x, well, that's just take each of the x values, multiply by their probability, and then add them up. So 0 times 0.35 plus 1 times 0.3 plus 2 times 0.25 plus 3 times 0.1, which ends up being equal to 1.1. So now let's find the variance of x. So remember, variance of x is equal to, and I'm going to use the shortcut formula, expected value of x squared minus mu squared. So to figure that out, I need to first do expected value of x squared, which means I got to take each of these x values and square them and multiply by their corresponding probabilities. So that's going to be 0 squared times 0.35 plus 1 squared times 0.3 plus 2 squared times 0.25 plus 3 squared times 0.1. And then finally, I need to subtract off mu squared. But remember, mu is just the expected value of x, which I calculated already. So minus 1.1 squared. And when I'm done, I end up with 0.99. Now the question says, find the expected value of 4x minus 7. So the hard way to do this problem is to multiply every x by 4 and then subtract 7 and create a new random variable. But that's a waste of my time. Instead, I'm going to use the properties of expected value. So expected value of 4x minus 7, is just 4 times expected value of x and then minus 7. Well, I already did expected value of x, that was 1.1. So it's 4 times 1.1 minus 7, which ends up being negative 2.6. Now to do variance of 4x minus 7, that's just going to be 4 squared times variance of x. And remember, the minus 7 does not affect variance because all the data got moved 7. The spread didn't get changed. So this is just 16 times the 0.99. So I end up with, now I'm going to give all the decimals here because I'm going to use that to find the standard deviation. So 15.84. Now because I already have the variance, I'm not going to try to find some special formula for the standard deviation of 4x minus 7. I'm just going to use sigma of 4x minus 7 is going to be square root of 15.84, which is approximately 3.98. And again, I use the properties of expected value and of variance of a transformed random variable to end up with the shortcut values for that one. And that's the end of the lesson.